Okay, welcome everybody to IBM Research in particular. Thank you for coming to our workshop today. And my name is Joern Ploennigs, working for IBM Research in the Cognitive Building group. And for today, I will basically start the workshop today with a short introduction of what this thing is about. And then afterwards we will have 3 other speakers, or 4 speakers in total, giving you a little bit more details about different aspects. So we have basically Nicolas Riault from Fraunhofer giving you more details about energy performance modeling. Then we have Jim Sear from Sustainable Energy Authority Ireland, giving you more details about basically the regulation and the opportunities in energy savings. And last but least, we got basically some practical experience from CIT, telling us a little bit more about what's the real life of a building operations and facility management person. And that's actually the preparation for the workshop that we will have in the afternoon, where we basically split it out in 3 different groups, work on different topics. And as you can see, there's always construction going on in IBM. We're a changing company the whole day and the whole time. And that's basically this layout of the workshop today. We chosen the title of Sustainable Cities, Energy in the Built Environment, primarily because we as IBM Research, we are the Smarter City Lab of IBM. So what you can basically see here, so IBM Research is quite a large organization. We have about 3,000 employees all around the world with 12 labs on basically key positions on each country, continent. And Dublin is one of the newest labs. And we really focus primarily with 100 researchers on smarter city aspects. And you see that here. We basically, when we started, we focused on smarter cities. Then we basically developed further into mini cities, so smaller use cases around cities. And we basically cover everything that you find in a city. That basically starts from traffic, water, energy, to including basically the buildings that each of us is basically occupying. And now we really transition to basically cognitive IoT, so Internet of Things in cities, and applying cognitive technologies to it. I will come to that a little bit later, what we think of that. And our competency is quite widespread. So we have basically domain experts, we have analytic experts with backgrounds in mathematics, with backgrounds basically in computer science, optimization people. So we really are on the analytic layer of a city. So we don't necessarily solve the technical problem itself. Our work starts the moment we basically get data, and then we analyze the data and we're looking for optimization potential. And that's basically the biggest, our biggest skill set. So you see that here, we have here about 6 focus areas that we're working on. As I said, it's transport in the city area, water, energy, mobility, so also like analysis of telco data, analysis of social data, and how can you basically transfer knowledge that you see, for example, in the social web to city operation. So that's one of these aspects. And then it's energy, buildings, and healthcare. There we're working strongly together with Joern, which is basically also located here. And the idea of a cognitive system in the end, within IBM, a cognitive system is a self-learning system. So it is able to adapt to new changes in the environment, and it takes the data that you find in the city, that is coming out of the city, analyze it, and is then adapting to it and helping you in improving your operation. And you need a cognitive system from our perspective because the city itself and the systems that we're dealing with are getting more complex and more complex every day. To basically come now more to the aim of the day today, I will want to talk about one of the main problems that we as a project team see in the energy buildings domain. So a common problem that you have is that you have some architects which have great ideas. They're using basically building simulation tools and estimates to predict how much energy a building is going to use. Then you start the construction, then you do the commissioning, and then you already see a small derivation from what you actually was planning. So your Class A building in the end is after commissioning maybe only a Class B building. And then you start operation, and over time, basically the building is deriving from this commission performance more and more and more. And that has many reasons. So that's starting basically with the people occupancy occupying the buildings. That's simply are failures in the systems. There are basically maintenance issues that you have with these systems. And last but not least, in Ireland, it's also like the weather is kind of predictable. It's going to rain. But the weather has this big influence on the building operation itself. So in a very dynamic influence. And if you really want to basically predict energy consumption in a building, it's very challenging. And we as IBM, you hear that, we're facing these challenges because we're basically operating our campus, our buildings here as well. And IBM is basically doing lots of changes. New groups are moving in. We are hiring 300 people, and your energy consumption is just jumping up. And these are basically the common problems that we are facing, which might make it very hard to predict and operate your buildings according to your plans. What we want to do within the TOPAs project, which is an H2020 European project, we want to reduce that gap. So we want to use the data that is coming out of the building to better be able to predict the building energy consumption and also to better act on things that we detect within the building energy consumption. And that's basically in the end leading to continuous commissioning. So instead of doing a commissioning once or every 3 years, you kind of use the data coming out of the building to continuously and automatically commission the building over and over again and be in that way able to track the performance of the building in an optimal manner. Within the project, we have 3 demonstrator sites. So IBM campus here is one, and we're basically using here, for example, our IBM research building. It was designed as a smart building research lab. So we have about 2,500 data points within this building. We are monitoring lots of things, and truth to be told, lots of data is not always good because we are really facing the problems of having too much data. So we are knowing too much about this building and we are not really able to analyze everything. So we actually need new approaches to analyze all that data. Another thing that we are basically approaching as a project is how can you design and what kind of equipment do you actually need to correctly monitor a building? So if you go out, particularly with IoT, your options are exploding. So you can basically get a very easy sensor for $5 and put it basically in your building, or you can get a very dedicated, very expensive sensor, and it's very hard to choose the correct devices out of this mass of devices. With wireless sensors, it's quite easy to install them in the building, but again, with wireless sensors, and we have a Zigbee network here in the building as well, we also facing then the problem of connectivity between the wireless devices. And that's actually where we provide within the project decision support to the people basically that have to extend their system, that have to design their systems, in what kind of devices they have to select and where they should deploy them. The next thing is when you want to deploy them, you want to have that as easy as possible. And truth to be told, not everybody is in the optimal position of designing a new building. In most cases, you're actually operating legacy systems. And it's very hard to get access to all these old systems. So that's one of these things that we're trying to target here in the project as well, is how can you make this integration as easy as possible, including integration of legacy systems. And our approach here is that we are using middleware technologies that are basically IoT enabled, that end up in a small box. You take this box, you connect this box to your BMS, and then it's basically pushing data to a database in the cloud. And the big benefit of having basically all this data then in the cloud is you can access it from everywhere. So all your different tools that you want to use for analyzing your building data can access this data in one point. And that's a big benefit here in the project. We are looking for an open BMS approach. That will be one of the questions that we are going to target in the afternoon. How can we realize such an open BMS system? What does it mean? What are the requirements for an open BMS system? And then the next step is to develop new analytics on top of that. So analytics that really help you in planning and maintaining your operation, and that do energy predictions, because that's the primary goal, because we want to reduce the gap, as well as basically doing fault diagnosis. So if something is happening in your building and you're not within the spec, operating within the specs anymore, that you're very fast in detecting that and very fast in solving that, because you actually know where this problem was coming from. And that's basically part of the actionable insights that we want to generate. So that you basically have a dashboard where you see the energy flow within your building, and you're always aware of what's going on. And you have a central point to do that. And this central point is accessible from your laptop, it is accessible from your mobile device. So there are not boundaries anymore, whether you are basically in your office or if you're basically on the site. And that's one of these aspects that we are looking at. And last but not least, we want to improve the performance of the building itself. We are using for this distributed model predictive controls. So we take all this data and we extract from this data models how the building is performing and operating. And this allows us to tweak the controls that the set points are just the right set points, and that you're really saving as much energy as possible in your operation. And that's basically in the end then closing the loop in the operation of the building. What we are looking today from you is input on these things. So we have this vision and we have this idea how such a system should look like. But we are not the world. So you are expert in the field, you experience these things day by day, and you have basically the input of all the practical problems. Where we only see a small piece of that, we are looking for your expertise and your answers across these fields. We in the end have 3 different working groups in the afternoon that are basically approaching 3 different topics. So one thing is basically on the energy management. So what are basically the energy assessment methodologies that you use in your daily life? What basically of these energy assessment methodologies is working good? What is bad about that? And how should we improve that? And that's in the end a very important input, because then we might even influence the policymakers with that and give basically back recommendations to the European Commission and to Sustainable Ireland to basically say, okay, let's improve basically the regulation in that way that makes your life easier, and on the other hand basically makes the operation and the performance of the building better. The next thing is topic is around system integration. I was already talking about this open BMS topic, because that's basically the topic I love most. And there the question is, how can we basically make a BMS system really open, that everybody who needs access to the data actually can easily access the data? Because when you work in building analytics, you always know there's an old system and installed by somebody, and very troublesome. It's very hard to access this data and analyze this data. And we want to overcome that. We really have that vision of something that basically collects the data, and where everybody who needs access, not everybody who has access, but who needs access to the data actually can access the data. And last but not least, the last piece is on building management itself. So where are the real problems in building operation from building management side and facility management side? So what are the pain points that you experience in your daily life? And how can we include that within this project vision and provide solutions that help you on your daily life? And that's the idea, and we will form 3 workshops in the afternoon around this. You see these flip charts, we then basically will split the group into these 3 workshops and work on these 3 aspects. So last but not least, I want to come back to our IBM perspective. Like I said, we are in the unique position that we are not simply a research organization like IBM Research, but of course, we are a big property owner. So we have basically buildings and campuses all around the world, not only research campuses. And we're also dealing with lots of customers that have similar problems, that really are basically have assets all over the world and need to manage that. And that's also, from my perspective, a little bit shifting the attention and the problem scope that you're dealing with. So our problem is not, how can I optimize one building? We're talking here, how can I optimize 100 buildings distributed all over the world, and how can I monitor them all together and solve these integration problems? And then you really have a big scaling problem, because if you already have a problem with analyzing and integrating one building, you have a humongous problem with integrating 100 buildings all over the world. And that's basically what our daily problem is, and that's basically what where we try to help customers in solving these problems. And that's why basically we're also trying to bring in this perspective of new solutions that help us to do that. And the last thing or the next thing is that Internet of Things is changing how buildings are structured and how they are operated. So from our perspective, you might have seen that in the news, that IBM is spending quite a lot basically on the cognitive field. So new technologies, artificial intelligence technologies and machine learning technologies that you utilize to better operate your building. And from my perspective, this is very important because it will change how we operate our building. So far, a building is kind of a silo. So you design it, you basically start operating it, and you're not really changing it for the lifetime of its operation of like 20 to 30 years. So you don't change the technology, you don't really change so much about the operation strategy, you're trying to tweak the set points, but that's it. But if you really want to save energy, and we have to save energy with buildings because they're already consuming 40% of the energy, and they have the biggest potential of saving energy in the world. So we have to overcome that. We cannot operate them in this static manner anymore. We have to be dynamic. And we have to be dynamic also in terms of the smart grid, because the smart grid demands that with the new regenerative energies within the smart grid. And we see that in Ireland. The moment basically we have a storm, half of this grid goes down because all these wind farms need to be turned off. And we have outages in Ireland. And you can actually use buildings to store energy. You can use buildings to basically balance the energy and the dynamic of the smart grid. And that will be basically one of the needs that we need to address with our building operation. And last but not least, when we think about this, we also can think of when we have a campus like here, then we actually can also think of new scenarios, how we operate the buildings individually within this campus. So why don't we basically optimize the buildings together and, for example, turn buildings on and off individually, and this way basically balance the energy consumption across the campus. And these are basically these ideas that we will have to approach and solve in the near future. And to do this, buildings have to become more dynamic. And more dynamic means that also you will install more sensors, more devices. This has to be done as easy as possible. You cannot spend a day for each device. It is, in the end, has to be something like 5 minutes. And that's possible with IoT. With IoT, you simply take a sensor out of the box, you turn it on, and it automatically connects to something on the cloud. And you can easily push the data to the cloud and analyze it there. So, and that will become basically into the building itself, from my perspective. And then basically when you have all the data, you cannot adapt your analytic system to this data anymore. So you cannot basically tweak your BMS system every day if you have a new sensor. So it has to be basically the analytic system itself has to adapt to these new data flows, has to learn from the data flow what is a good building operation and the good building energy consumption, and then basically optimize its operation to this. And that's basically in the end the last step, which is basically providing insights in the building operation, that you basically help the operators on the one hand by automating many of these tasks that you're dealing with today, and enabling you with better insights to really operate the building with knowledge and not just with experience. Because I know each of you is very experienced in building operation, but in the end, there are systems that can help you to operate your building better. I will give you one example. That's something we are working on, among other things, which is basically an energy prediction problem. So that's directly approaching the gap. So when you want to minimize the gap, the first step what you have to do is monitor the energy consumption of your building. So, and the second thing is then when you want to compare and identify if your building is operating good today, you have to compare it to the operation of the last days. Normally you do that by experience. The problem basically is, in this case, you need experienced operators that are able to do that. And from our experience with buildings, it's actually not that easy, because in our case, for example, the campus usage changes day by day. So a typical thing is actually IBM has a work from home policy, which leads to the fact that there are less people at work on Friday. People come late on Monday. And in the end, people don't come at all during summer months. And we actually see a direct correlation between how many people are in a building and the sunshine outside and the temperature. Because the moment the temperature goes up, people say, oh yeah, I'm going to work from home. So, and that's basically these things that you actually need to consider if you want to operate a building correctly and if you want to predict the energy consumption of a building correctly. And that's then getting very complex. So you need something actually that does that for you. And with machine learning, you can actually realize that very easily. So you can easily create machine learning models that do just that. The problem with most of these models are that they are black box. So you don't really know what's inside the model and what it actually learns. And that's not good because you cannot really trust the outcome. If you don't understand the system, the outcome is not very trustworthy. So you actually need a model that on the one hand is able to learn all these different influencing factors, and on the other hand is easy to understand. And we developed such a model, it actually, what it does, it decomposes the energy consumption into its individual influencing factors. So you see that on the left-hand side, it's showing you basically, for example, different time of days profiles for Friday and Saturday. And you really see that basically on Friday you have this typically office hour curve, energy consumption curve, and then you basically have a very low energy consumption on a Saturday. And you also see the dependency on the temperature and the solar radiation. And these are actually the things, so you actually see, you can see these transfer functions, you can interpret these transfer functions, and by this you are able to better understand the energy consumption of the building and what actually are the influencing factors. And the next step, what we do is quite simple. So we use these models to predict the energy consumption of a building. And you might have noticed that IBM just acquired the weather company. So what we're using for this is simply weather forecast data from the weather company. And this allows us to quite precisely predict the energy consumption for your building for the next 2 days. And then basically each day we compare the UV consumption against this profile. You see that the prediction is the band in the middle, the blue band, and the red one, that's actually the real energy consumption. And you see that it's abnormalous. And then the trick is not to only detect that you have an anomalous energy consumption, to actually diagnose where this anomaly is coming from. And that's actually then the more tricky part. And this basically video will simply show you how such a system, the system looks like. And you see here some dials that just allow you to easily monitor your building performance. As long as they're in the middle, in the green space, everything is okay. And if they're going in the red area, the building energy performance is bad. You see a calendar view that gives you a very easy overview on the left-hand side about your good days and your bad days in terms of energy consumption. Here you have the time series plot for 1 day, and you actually see like new data is coming in comparison to our energy prediction, and that's a good day. Everything is more or less basically within the prediction range, so there's nothing to worry about. And that's the day that you want. That's a day basically where you're sitting at your desk, drinking coffee and thinking, whew, that's not a problem, that's an easy day today. So, but most of these days are not that easy. So in most cases you actually have anomalies. And what you see here, that's the energy flow of the day. And if you look closer, and this actually is to notice that the energy consumption of the UPS and the HVAC unit and the lighting unit is more or less the same. So it's the UPS is basically the main energy consumer, but there's nothing anomalous about this. And you can use basically this energy flow view to easily identify which are my biggest consumers and how is actually the energy flowing through my buildings and through my campus. And here you see the models itself. So you really have these transfer functions explaining to you how your building is consuming energy and what are the depending factors for this energy consumption. And then we will basically see on the next screen, I think we're going to an anomalous day. So the day is nearly ending, and now basically the next day will be anomalous. So we will see a huge energy consumption on a day, and that's the data set that we took from our campus. So that's basically really what is happening. And you see that here. So our prediction band is the green band in the middle, and that's a weekend. So that's why the energy consumption is very low in total, but the real energy consumption is way out of bounds. So something is going on. And something is happening, and you want to know what. So, and the problem is basically when you now look into in the energy flow. So now we basically have this anomaly, and back to the dice. Basically, the dice show you that you're out of bounds, and that something is going on in your building. And so that's what you see here. So everything is red as it should be because you have a too high energy consumption. And, but the interesting piece is actually if you look into the energy flow itself of the building, because you will notice with a sharp eye, if you looked basically on the last energy consumption of the previous day, there is no huge difference. So if you just look into the energy flow, it's not easy to identify where my problem is coming from. And that's a typical problem that you're facing in a building when you have a problem. You know you have a problem, but you don't know where it's coming from. And the nice thing is basically if you then look into the diagnoser, he figured out this problem is actually was coming from the air handling unit, which was incorrectly scheduled. And I just basically added the air handling unit to this time series plot, and it detected basically this anomaly, traced it back to the air handling unit, and told you, please fix this air handling unit. And what we basically do to do this, we simply link it to Maximo, that you directly release a work order in Maximo. You directly have a maintenance guy going out to check the air handling unit. And that's basically a system which allows you to do that within half an hour between detecting the anomaly and fixing the anomaly. And that's only one piece of things that we're going to develop within the project that helps you to better operate your building. And that's basically also the last piece that I want to show here in the morning session. And I'm now open for your questions.